So the next talk I've got is determine the best shard key. And I wrote this the weekend. And it took me far too long to write, to be fair. So does anybody know what a shard key or partition key is? Just raise your hand. Few people unsure? OK. So a shard and partition key is a way to horizontally scale your application in a stateful environment. So if you think about web servers are usually stateless. So you can put them behind a load balance and just spin as many you want up. You don't really need to care. If you want to kind of like store your data with fast reads and fast writes, you need to scale them on multiple nodes within inside your environment and be able to kind of know where each of them, your records is on them, like nodes. So the key determines like where your data is being stored across them nodes to start off with. And the key is usually ideally based off something which is known within inside that record or that row or that object. So it's probably better easier to kind of show you a picture, but these are the kind of all the products which I kind of throw together on a slide. So we got like Cosmos DB, Cassandra, DynamoDB, Azure Service Bus, Kafka, table storage, MongoDB, loads and loads of products that use like partition and sharding, and they're all a bit different from each other. And we'll go into that in a minute. But the concept is kind of all the same for them all, and you have to think about the similar things for them all as well. So this is a bit of an example of how sharding kind of works, or partitioning works. So say we've got Liam, for example, and he's 35. So these are all the shards we've got. So these shards are classified as like VMs or nodes or Docker containers or anything else where you want to kind of you want to partition your data and run the database engine, for example. And shard 1 is ranging from 0 to 33, shard 2 is 34 to 66, and shard 3 is for 67 to 100. So Liam, for example, would go in shard 2, so we'd put him over there. So when we write Liam's record, we know he's on shard 2. Olivia would also go on shard 2 as well, so we just put her there. Noah would go on shard 1 because he's 21, so he's less than 34. Oliver would also go on shard 2, and Charlotte would go on shard 3. So this is kind of how it all kind of works in every single system, really. All it's doing is getting that bit of data and funneling it off onto some node somewhere based on some kind of key. I've got another one, Robert. So yeah, Robert goes on shard 2 as well, because he's 55. So I hope that kind of makes a bit more sense than me talking. There's also a concept of balancing on some kind of database engines as well. And MongoDB has this, for example. And what it does is try to move the data around. So like shard 2 is very packed full of data at the moment. So what it's do is kind of alter the range of the age. So now it's 0 to 35. And then that'll be the 36 to 66. And then what I do is move them records across to it. So then it's nicely balanced evenly across all your shards or nodes. And it can do the same thing for the upper bound node as well. So you can just move that across to there. And that's a concept of balancing what some storage engines have and some don't. Some just don't really care. So it can be quite problematic kind of using a sharding partition key as well. And this kind of happens a lot because people don't really understand. They just whack, I don't know, a static GUID in there and hope for the best. Or just put your company name in there, or just put some value which is just the partition key, so the partition key is always the same, which is obviously never going to scale. So the first problem is hot partitions. So say we've got an example where we've got the age ranges again, and we've got shard 2, which is obviously going to be like very busy compared to the other shards, because the range of people, like there's less people aged of 0 to 33, there's less people older because they've died and things. That's not nice. And like in the middle, there's loads more people, active people on like probably the system, because they're in that age range of kind of using the platform really. I shouldn't have said died. I should have said old people didn't use the system. But yeah, so this one in the middle is going to be really hot and busy all the time. So that's called a hot partition. So these two shards at the side, 1 and 3, are going to be doing no work. And the middle one's just going to be getting hammered all the time, doing all the work, which is not going to be very scalable, obviously. There's also this thing called low key frequency. So say all of our people all are 35. We can't put them anywhere else except for shard 2. So they all get placed on shard 2, and shard 1 and shard 3 is not doing anything. And then if we get more, which are just the same age, then you can't really do much about it. You can't even balance this. So even if you have a database engine which can balance these nodes out, you can't put 35 into shard 1 because 35, they'd all have to go to shard 1, right? It just doesn't make any sense. So we need to kind of have high key frequency, really. The other one is low cardinality. So this is where you've got a limited amount of options. And I know there's multiple genders, but for this example, we're just dealing with female, male, because that's what the system has. And so we don't have any way to kind of split these up. We either put them on shard 1, which has got males, or shard 2, which is just females. And it might split out across 2 shards, but say we want to scale the system out further because these ones are getting too much overloaded. We put it in shard 3 and shard 4, but what genders are they going to have? Because we can't split the males up and we can't split the females up onto shard 3 or 4 because they can't all move together. So it doesn't make any sense. Another one is monetarily increasing or decreasing keys. So this is where people usually end up using IDs, like sequential IDs, or using created at dates, which are obviously not a very good shard key. And the reason for this is because you start with shard 1 and 2 and 3 and 4. And these got 1 to 10, 11 to 20, etc., all the way up to 21 to the maximum. And these are all nicely spaced out for the moment. But we got 31 to add. So we go put 31 in shard 4, because that's where it goes. We also put 32 into shard 4. And we also put 33, and you see what the problem is going off here as well, where everything just ends up on the end shard. And fair enough, if it can balance the data out, it could move it around, but then you put an extra load on the database server for no apparent reason. So the more writes you add to this system for the end shard, it has to also then have to move it all around and rebalance everything again, if it can do that. So having monetarily increasing or decreasing shard keys are never a good thing. So even if it is decreasing, you'd end up on the left-hand side instead. The next one is bad query patterns. So let's say we've got our shards, we've got 5 shards this time, all different age ranges up to 50. But we want to find what partition M is on. Anybody got a clue where M is and which shard M is on? 4? I don't know. So you can't determine, you can't even narrow down your query. You'll have to do a whole cluster scan. So say you've got 100 shards in your cluster, you'll have to scan all 100 of them to find where Emma is. You just don't know. So you need to be able to use kind of something which is part of the partition key to deal with that. So that comes to the patterns of shard and partition keys. So they're the kind of problematic things. So the things what we want to look out for are high cardinality, high frequency, not monotonically increasing shard keys, and also understand our query patterns as well and what we're using. And we might need to also pass in extra data into the query so we can actually figure out what node it's on as well, which is quite common, which you wouldn't do with SQL Server, for example. So one of the things we can do is compound fields together to increase cardinality. So for example, this is a bunch of athletes and their ages and what race they ran. So the first athlete 1 ran the Sheffield Marathon in 2022, the full one. 3 did the half. And then there's also the York Marathon, York half as well. So that allows us to kind of create a higher cardinality over the data set for the partition key. And it also decreases in cluster scans as well. So if you want to find, for example, Jesse, who ran in 2022 in Sheffield, we could actually limit the amount of records we want to scan by giving the actual partition key, so partial partition key. So we could say where the partition key starts with 2022 _ Sheffield, which gets the Sheffield in 2022, and then we can just scan these 3 records, and we'll be able to find him a lot more efficiently. So we're not scanning the whole cluster, we're limiting the amount of scanning across the cluster. We can also use a thing called hashing. So instead of just using the sequential IDs or the create@, we can hash that through some kind of hash function, and it'll distribute the actual records evenly across the node instead. So for example, Robert can come in, he's got an ID of 31, but this time he goes on to shard 2 because his ID is hashed and he's got hash 2. Oliver comes in at 32 as well, and then that also gets hashed to hash 1. So as you can see, it's getting spread out easily across the system because it's hashed and you're not using the sequential IDs. So that's one way to get away from, if you need to use monocollector increasing kind of IDs or values, you can hash them instead when you create the partition key. You can also do range keys to decrease cluster scans as well. So for this example, we've got a partition key, which is discount. And say we want to find products where the discount, all the products where the discount is greater than 10 and less than 25. We can use the partition key to do that. We can just like go search it and pull back the actual products for them. So, as I said, every database is not the same, which is a bit awkward. So DynamoDB hashes all its partition keys. So you can't use range-based queries on your partitions. Table storage in Azure, I don't think does that, and allows you to actually query across partitions as well. But it actually creates it's just split partitioning, so it'll try to group partitions together as well if there's single items in them partitions. So one of the main things is always read the docs. And one of the most flexible ones I've ever used across like all the cloud environments and everything has always been Mongo, and I like Mongo. So that's it. Thank you for listening.